Hello, and welcome to Indie Dev Tools. Today, we're talking about game objects and the scene graph. Game object is a class that holds a bunch of data, things like where it is and how big it is. It can be extended into things like sprites and shapes for drawing, or used as is for collision objects, or just as a node in the scene graph. The scene graph is how we organize game objects in hierarchical parent-child relationships. Each object is a node in the scene graph and can have one parent but many children. The render function will look through the scene graph in a depth-first fashion, checking all of the children of each node it comes across and drawing it if necessary before moving on. Here's a simple example. There are different ways of doing this, but my scene graph would probably look like this. At the top is the stage. It holds all the other game objects. Next, we have a simple repeating background. Though created with tiles, at runtime it is one large image that draws itself repeatedly to fill the screen. Then we have some platforms. Once again, they're created with tiles, but at runtime they will be pre-calculated into larger blocks to reduce collision tests and draw calls. And then we have some characters. Each character is usually a collision object with a sprite as its child. So let's take a look at some code then. We use a lot of vectors here, which we covered in the last video, so you may want to check that out if you aren't familiar with them. To start, each game object has a unique ID. Each has a position and a size, often measured in pixels and stored in vectors. The position will either measure from the world's origin or the position of the object's parent. Objects can be rotated, so we have a rotation property that measures the rotation in radians. We also have a pivot point around which the objects rotate. It is stored in another vector which defaults both values to 0.5, or the center of the object. Objects can be scaled on their x or y axis independently, so we will use another vector here, defaulting both to 1 this time for normal scale. Simulated physics is common even in simple games, and the velocity and acceleration vectors accommodate that. Velocity is how fast the object is moving, and acceleration is how much it is speeding up or slowing down. Objects can be drawn transparently with the alpha property, or simply turned off with the visibility property. Alpha, set to 1, draws normally, but set to 0 it becomes fully transparent, while visibility just takes a true or false. Each object also has a blend mode similar to the blend modes in Photoshop. We talked about this in the first video on canvas operations. As mentioned earlier, each object can have one parent, though it defaults to null, and can have many child objects, held in an array called children. The z-index property is used to sort objects, so they are drawn in the correct order. The underscore signifies that it's a private property, and you shouldn't access it directly. We'll write functions for that shortly. Circular and points are useful for both shapes and collision, and I will explain them more in the coming videos on those subjects. And finally, we have a debug boolean. If true, this will just draw a red outline around the object and a black point at the center. This is useful to figure out where the edges of a collision object or a sprite actually are. Here we have a bunch of properties created with getters and setters. These are mostly just helpers that will shorten our code in other places. The first 8 are sets of 2 that allow us to access the position and size vectors as x, y, w, and h properties. These are just personal preferences, but it allows you to pass any game object as its position vector, which I find useful. Then we have properties that return half the width, or half the height, a vector at the center point, or a vector at any of the 4 corners of the object. Half width will also be used as the radius for circular objects. The G in GX and GY stands for global. They add the object's position to its parent's global position to find the global coordinates of the object. The z-index getter just returns the z-index variable, but the setter will cause the parent to sort its children in case altering the z-index changed their draw order. AddChild takes another game object, removes it from the scene graph, and adds it back as a child of this object. It then sorts its children to make sure they display in the correct order. RemoveChild splices a game object out of this object's children array, or throws an error if it is not a child of this object. Finally, the update function just adds the acceleration vector to the velocity vector, then the velocity vector to the position vector. If you change either the acceleration or the velocity and call update in your program, it will cause this object to move around the screen. That's all that's currently in my game object. Sometimes I add other things if a game needs it, and when making tiny games for jams like the JS13K, this gets cut down pretty dramatically. I will extend it into shapes for drawing in the next video, and sprites for drawing images and animating them in a later video, but we still need to cover how the render function looks through the scene graph. The render function first clears the screen, then it looks through all the stage's children and calls display object recursively on them and all of their children. Here's what display object does. First off, this only happens if the object is visible. If it is, we save the context so we can return it to this point later. Then we translate the context to the pivot point, rotate, and scale it. If the object has a blend mode, it is set, and if it has a render function, it is called. Shapes and sprites will have render functions, and you can add your own custom render function if you want. If the object has debug set to true, we draw a line around it and draw a dot in the center. And finally, if this object has any children, it will call display object on them, but only after translating from the pivot point to the top left corner, as that is where children's position is measured from. When all of this object's children and all of their children have been processed, the context is restored to its old position and the process begins on the next object in the scene graph. Before we go, here's a quick example, which of course my computer did not enjoy screencasting. It just creates a couple game objects with debug turned on so you can see them, and an invisible game object that is moved to the mouse's position every frame. When you click the mouse, if it is inside one of the other game objects, it will be added as a child of the mouse object, causing it to be moved around as well. Links to the code and example page in the description. Thank you for watching. If you enjoy these tutorials, please like and subscribe or consider supporting us on Patreon.